Sounds not so bad. My first time in this room, actually. Usually I'm on the other side, the 22 room.
The one that's straight across.
Yeah. This wasn't going to be my class though, because Dr. Miral was going to teach this one, but yeah, he's not here anymore, so they asked me to step in.
He lost Bayro and Robson.
Well, Dr. Robson will be back. She's just on sabbatical.
Oh, yeah. Yeah, but it's just crazy because they're both the people who.
I know, I know. All of the senior design faculty kind of um are not available this semester for one reason or another. Yeah.
Same. These lectures are recorded as well, right?
Yeah. Mhm.
Thank you.
Like all of them, or what type is going to be?
I got,
What's seasonal?
double check, it's just. I don't know, yeah, it's like a lot of them. Like I've never had bigger.
Oh.
Never had them?
That's not.
Which one's getting with the barbecue, like?
I got it. Okay.
If you go straight to us.
I think it would. Nah, I just. I just feel like. I never got mine. It's gonna like. Yeah. Yeah, I don't think it's more. We can say we should. What's it called? At least just store it in my class space. I'm sure. Hours.
I switched out my economics. Eight down. I got she has economics teacher.
Well, because of.
But he the one I push it to end up going half the time.
Yeah, it's always.
Yeah.
Really. Had bad reviews on it. Yeah. There's never will be.
No, I first started. I'm not a lot of just. That's good. There's always. Yeah, I think
No, it's water made.
honestly, I feel like it was like.
That's what I expected. I heard with the carbonics this morning.
Yeah, I was like, it's perfect.
I feel like trying to do that, so that's what
All right, it's 4 o'clock. Let's go and get started. Hi, good afternoon, everyone. How's everyone doing today? Good to see you all. I know probably didn't expect to see me here. This is not a class I usually teach, but I was asked to fill in because Dr. Merrill doesn't work here anymore. But this is a subject that I'm very familiar with, and so very happy to be here, very happy to be teaching this. So if you haven't met me before, my name is Professor Justin Tran, and this is EGME 436, Introduction to Computational Fluid Dynamics. So we're starting the semester a little bit late just because of the holiday on Monday. So I think, like I mentioned in the email, normally on the first day I'd like to just do a brief introduction. We'll talk about the syllabus, the course website. But I do want to start a little bit of content today. So my plan is for the first 45 minutes to be just introduction stuff, syllabus, course website. And then for the last 30 minutes, we'll kind of start the first lecture. And then of course, we'll continue it next week. Okay. Okay. All right. So first, let me just introduce myself a little bit in terms of who I am. So I don't know why the first thing I have here is my office, but my office is in E220. So if you're not familiar, that's the engineering building right over there. The second floor. So if you go up the elevator, you just turn right and you just keep going to the corner. That's my office. My email address is justran@fullerton.edu. I've been accused of stealing this email address from a running club here at Cal State Fullerton, but it's just an unfortunate combination of the letters in my name. So you'll be emailing that a lot. Email is the primary way that I ask you guys to contact me, other than just talking to me in person. So if it's in the class, you can come talk to me. I don't bite, I promise. But outside of class, feel free to send me an email anytime. I grew up in Cyprus, and so if you're not familiar for where that is just about 12 miles west here on the 91. So I'm very familiar with this area. I had a bunch of friends from high school come to Cal State Fullerton, so this is pretty much home for me. My college career has kind of taken me all over California. So I did my bachelor's at UCLA, my master's was at UCSD, and my PhD was from Stanford, all in mechanical engineering. And my research interests are actually pretty applicable to this class. And so what I do basically is I do CFD of blood flow. And I do that to study heart and blood disease. So we'll probably talk a little bit about that, in terms of application, probably later on in the class. So that's why this class is kind of exciting. Okay, learning objectives. So, if you've had me as an instructor before, you probably are very familiar with these, but I like to start off every class with a list of learning objectives for the day. So there will always be about 2, 3, 4 of these learning objectives. Usually I'll display them before the class starts. And so if you come early to the lecture, I always recommend you write them down in your notes. So the learning objectives, you can think of them kind of just on a very basic level. You can think of them as kind of like an outline of the topics that we're going to cover for that day. Okay. So I have every lecture note, everything is kind of organized around these learning objectives. And so, I always tell students it's good to write these down at the head of your notes, just so you kind of know what that notes are going to go over for that day. And you're going back and studying for the exams or doing the homeworks or whatever. Okay. But I also write these learning objectives for another purpose as well. And so if you notice, both of these learning objectives that I have here, they start with a verb, right? And that's very intentional because I write these learning objectives in a way to describe to you, what kind of skill or what kind of knowledge that you should be able to demonstrate by the end of the lecture today. Okay. So for example, the first learning objective that we have here is to describe the use and utility of simulation tools for performing engineered work with fluid mechanics. And so by the time you leave this room today at 5:15 p.m., you should be able to do just that. Okay. And just to give you a little bit of a preview too, I like to use these learning objectives as exam questions too. And so, these are kind of good tools for you to study for the exam. Okay. Obviously not the second one. I'm not going to ask you questions about the syllabus on the exam, but I had to put something just to say that we're covering the syllabus and the course website. Okay. But definitely get used to these. I think they're a good way to kind of organize your notes, organize your knowledge, and they're a tool for me to organize the classes. Okay, so let's start talking about this course in terms of what it is, right? So what is computational fluid dynamics and why is it important? Okay. So when you say computational fluid dynamics, it's not really just a specific software or a figure or anything like that. Really, CFD refers to a collection of numerical and computational techniques for simulating fluid mechanics phenomena. Okay. And believe it or not, there's actually more than one way to accomplish this. And so, for this class, we'll be focusing on one particular technique, probably the most popular and I would say most effective technique, but there are other techniques as well. Okay. And so the main idea here is to, kind of leverage the power of computers to perform these algebraic and arithmetic calculations that kind of far exceed what we can do as humans. Okay. And so through this, we're able to take a subject, fluid mechanics, that is notoriously very difficult. The governing equations for fluid mechanics are very hard. I don't need to tell you guys that. Everyone here has taken fluid mechanics. But computers, what it allows us to do is it allows us to solve these very difficult equations on very complex geometries and very complex situations, very complex boundary conditions, very complex loading, which is very common for fluids. And so, for fluids, we have very complex loadings, boundary conditions. We can add turbulence in there. So, basically any practical work that you're doing in terms of like engineering design or analysis with fluids, nowadays you kind of have to use CFD for it. There's kind of really there's kind of no other way to analyze it unless you're doing experiments. Okay. And so through this, we are able to do all the really cool modern engineering work with fluids in terms of, design, analysis, on these really practical systems that you otherwise would not be able to do without CFD. Okay. Okay, so just to kind of give you an example of the scale. So, what I'm showing you here, this is just a very simple pipe flow. So we have flow, pressure-driven flow in a pipe. So we have pressure on one end, pressure on another end. If there is a difference in pressure, then that's going to drive flow from one end to the other. Okay. This is the type of problem you would probably see in your 333 class, your fluid mechanics. This is one you can very easily solve with Navier-Stokes. But if you start to get into more complex scenarios like this, so this actually here is a screenshot from my research. And so what this is showing you is kind of an experimental cardiovascular surgery, actually. So, so just to kind of give you a bit of background, this blood vessel right here and this blood vessel right here, I don't know why it's blue. Normally these two aren't connected, but we've actually connected these two with a shunt for certain patients that have a single ventricle. So that's basically patients with only half their heart working. And so they need to do some, you know, casually speaking, we have to do some plumbing on their blood vessels to make sure that this person has a fighting chance to be able to survive with only half their heart. And so one way we do that is to connect these two blood vessels to kind of basically, give a little bit of extra energy, a little bit extra flow to this blood vessel here. Okay, so you can see in the situation we have very complex geometries. Blood vessels are not straight pipes; they are kind of very smooth and contoured, and kind of have a weird shape. And so we wouldn't be able to analyze a system like this without CFD, especially with kind of complex. You can see here we have a little bit of turbulent flow coming in here. We have kind of a jet here that kind of splits off into two jets here. We have one that's kind of impinging on this back wall. So this is something where you need to have CFD in order to analyze properly. Right? And of course, there's many more applications as well. But this is just to kind of show you that there's a huge range of complexity in terms of these practical problems. Okay. So speaking of fluid mechanics, these are the equations for fluids. So hopefully this brings back some good memories from fluid mechanics. So this is the Navier-Stokes equations, which Navier-Stokes refers to the conservation of momentum in fluids. And we have the continuity equation up here, which is the conservation of mass. Okay. So these are very complicated partial differential equations, nonlinear partial differential equations, which are not able to be solved normally. And so, we can solve these in kind of very simple situations, but, for most practical cases, you can't really solve these equations without a computer. Okay, so let's talk more about some applications. And so, these are probably two applications that I think probably a lot of you are probably interested in. So on the left, we have an automotive application. So automotive design is very heavily influenced by the aerodynamics of the airflow that go over the car. Because the amount of drag that you have on your car, has a lot to do with the fuel efficiency, with the top speed, the performance, and with how complicated car chassis are. You're basically unable to really analyze them without CFD. Okay. The other image that I have on the right there is a very simple image of an airfoil. And so that is obviously an application from aerospace engineering. Aerospace engineering and CFD kind of go together hand in hand as well. So, if you're going to be doing any kind of design or analysis of aircraft with, complex turbulent airflow is going over it, you need to have CFD in order to properly analyze it. Otherwise, it's just not possible. Okay. All right, so but there's also applications in environmental engineering as well. And so on the left here, we have kind of a large scale CFD simulation of airflow over a very large region. So, a lot of the weather predictions that you see on the news in terms of, predicting which way a storm will go, all CFD plays a role in that. You need to be able to model and predict, which way the winds are going to blow and how that's going to affect your weather. Okay. And on the right there, you can actually see a CFD simulation of a windmill that is producing power as well. So, CFD obviously plays a big role in designing those kinds of structures as well. Okay. Let me pause here just because these are nice images as well. Are there any questions on anything so far? Good. Okay. All right. So, like I mentioned before, if you're going to be doing any kind of practical work in fluids, no one really does calculations on pencil and paper anymore. You really kind of fall into two categories. And so you can either do experiments or you can do simulations. Okay. And so if you're taking an experimental approach, your goal is to try to recreate the fluid flow conditions in real life and measure the results, right? And so a very common way to do this is to do have like a wind tunnel, which is kind of what you see on the right there, right? And so with the experiments, experiments are always great for getting accurate and reliable data because there's really no disputing an experimental measurement because it actually happened. There's very few there's very few room for error in that sense. But the downside of running experiments is that it can be very time consuming and expensive to set up. So oftentimes you'll see a situation like this where you need to create a prototype. This is probably not a full scale airplane here. This is probably a scaled down version. But even creating that prototype takes a very, very long time, right? And so usually, practically speaking, you have to do experiments. You can't just fully rely on simulations to do your engineering work. But you oftentimes want to limit the amount of experiments that you do, because you can't really afford to be doing a ton of these types of experiments. And so I would say the bulk of design work, bulk of engineering work with fluids nowadays happens in simulations using CFD. Okay. So a lot of times, people will use CFD to run a simulation on airflow over an airplane and use that to iterate on designs. And then, usually that's done, 90% of the work is done there. Once you feel pretty confident about design, then you'll take your results from CFD and then you'll apply that to an experiment to try to verify whether what you got was good or not. Okay. And so both of these techniques are needed. You can't just run simulation and, there's practical restraints on, you can't just run experiments as well. But sometimes, in the fluid mechanics community, there's kind of a, I would say, I kind of call it like a sibling rivalry between the people who do experiments and simulations, but there's no one that's better than the other. You need both really in reality to do work. And this class, we're focusing on the simulation aspect. Okay. All right. So, another question that I get asked, in terms of classes like this, where, we're not just going to be learning the software, but we're actually going to be learning the theory behind, what goes into the software. So, why are we bothering to learn the theory? Why are we learning to bother kind of the computational techniques? Okay. And so, doing CFD is more than just using the software. Right? It's more than just using OpenFOAM to run a simulation and generate a nice plot. Okay. Because it's important to remember that, these simulations and these softwares are simply just tools for you to perform engineering work. Okay. And just like any tool, it has limitations and best practices that need to be properly understood before it can be used effectively. Okay. Because the thing with simulations, and if you have experience doing FEA or ANSYS, and so you would know this very well, it's not going to work all the time. And so, there's plenty of ways for a simulation to go wrong. There's literally millions of different errors that can show up. And so in order to, use it properly and to debug these errors, you need to have a firm understanding of the fundamentals behind the technology so you can debug these problems and, get reliable results. Okay. Because my goal, by the end of this class is for everyone in this class to become experts in CFD, right? So I want you guys to leave this classroom. A lot of you guys are graduating this semester, or you're graduating this summer, or you're graduating in the fall, right? And so if you're going to be going to a company and doing CFD work, I want you to have the confidence to say that I'm an expert in this. It's more than just being able to push the buttons in the software to get the pretty pictures, but you want to be able to say that I really understand this tool, all the limitations, all the theory behind it. So I can apply this to lots of different applications. Okay. Okay, so to kind of give you an example of kind of why it's important to learn this conceptual background knowledge, let's take a job that I think probably a lot of us have experience with, is a vet, right? And so if you've ever had a pet you've taken to the vet, you know that the vet has to have a lot of these what I call procedural skills, and so they have to know how to give a shot to an animal. They have to know how to take a blood sample or performing eye and ear checks, right? So this is generally what we expect our vet to do. But the vet, we also expect our vet to also have conceptual knowledge as well. So for instance, they have to know why they're giving your animal a shot, right? They're not going to say, oh yeah, I kind of feel like giving them 3 shots today. And then you're like, why? This is my cat, don't just give them random shots, right? So we also expect them to know, if our animal is sick, they have to be able to diagnose that, to tell us, what is causing them to be sick, what do we need to do to get them to be better, right? We need them to understand how to interpret animal behavior. We also expect them to come up with new treatments, maybe not the vet down the street, but veterinary researchers, we expect them to do that, right? And so, everything on the bottom there, those are not just, very simple, just press the button, get the result, right? These are, this takes a lot of understanding of the fundamentals behind, animal physiology, right? And it's kind of the same for us as engineers. So not only do we know how to use, we're expected to not only know how to use our tools, but to really understand them on a deep level as well. Okay. And so I think the last thing that we'll talk about before we jump into the syllabus is just talking very briefly about the general CFD workflow. Okay. So in this class, we'll be using a software called OpenFOAM. And so I would say probably in the second half of class, that's going to be kind of the predominant focus. And so this workflow is something that you're going to become very familiar with. Okay. So the first step in any CFD simulation and kind of really any computational simulation is to do what I call kind of pre-processing. And so pre-processing, that includes things like defining the problem. And so defining the geometry and the boundary conditions, right? Identifying the governing equation. So that is the mathematical modeling. The third step, mesh generation, that one's very important. So we'll spend quite a bit of time in terms of that. And so if you run any kind of computational simulation, you have to discretize your domain. And what that means is basically taking your domain and breaking it down into a bunch of, really tiny shapes. Okay. And all of this is done in preparation for the solution step. Okay. Okay, so the second step, broadly, we can call the solution step. So this is actually the step where you actually do the least amount of work. This is the part where the computer is doing a lot of the work. So we basically, once we've kind of set up the problem, we've done our pre-processing, we kind of just hit go, and we just let the computer do its thing. And so the only thing that we're kind of doing is we're kind of just monitoring it to make sure that, things are going smoothly in terms of what we expect. Okay. And then the last step is the post-processing. And so, whenever you run a computational simulation, the results that you get directly from the solver are usually not, I would say, I call it directly useful. And so there's a little bit of post-processing, a little bit of visualization that you have to do in order to produce plots like the following that you can actually interpret and actually use for engineering design. Okay. Okay, so those are kind of the three general steps. So the pre-processing, the solution, and the post-processing. And so, of course, we'll be going over these in a lot more detail throughout the class. Okay. So let's talk kind of briefly about different CFD codes. And so, there's lots of different software out there that can run CFD. In fact, it's kind of the claim to fame that a lot of people want to write their own CFD code and have it become famous and have everyone use. Okay. And so we're not going to go through all the CFD codes out there because there's literally a lot of them. But I do want to kind of make a distinction between two different kinds of codes that you're most likely to experience out in the wild, so outside of this class. And so the first class of codes are what I call commercial codes. And so these are the type of codes that you spend money on. And so, usually for most companies use kind of like an active subscription model. So you kind of have to renew the license for these softwares every year. That's kind of how these companies make money. Okay. And the benefit of a commercial code is that they are actually developed by a company, and they actually have full-time developers that are paid a full-time salary to support the software. Okay. And usually these types of softwares have more, I call them kind of bells and whistles, which are, a graphical user interface that you've got to click around. They actually have a support team that will answer your questions if you email them most of the time. Okay. Which is really, really nice because, a lot of times, you want to have these kind of nice features. The downside to these is that, these softwares, because CFD is a very niche subject, and engineers to develop the software is very expensive. And so, the cost for these softwares is often very expensive. And so the cost for some of these softwares can go upwards of $10,000 per year per license. And so, it's really not practical for individual users to have a commercial code. Usually the way that people get access to these commercial codes is that, your engineering firm purchases a group license. And then the whole company kind of uses it. So, this is not really, there's a few people that do this, but, very few people have a commercial code just as a hobby. Okay. The more common way that people use CFD, especially in kind of small settings, is to use what I call open source codes. Okay. So open source codes, these are codes that are free for anyone to download and use. And they're often supported by a group of community or a community of users and developers. Usually these users and developers are not paid. So a lot of times these are people that develop the software in their free time as a hobby, which is, very great, very passionate of them. But then also that means that they also have probably something else that pays the bills. And so, usually they're not going to be as responsive to questions, if you need some support. Okay. So oftentimes, these open source codes are supported by government grant funding. And so you'll see that, different research groups at universities develop their own codes and they make it open source as kind of a stipulation by the government. So those are usually kind of the best case scenarios. And the downside of using these open source codes is that, they're usually a bit more difficult for the average user just because, there's no graphical user interface, there's no bells and whistles, right? I think, it's not an experience like using SolidWorks or like using ANSYS where, there's a program you can launch and an interface for you to use. It's a little bit more difficult than that. And so I mentioned that because, the main software that we're going to be using for this class is OpenFOAM. And so OpenFOAM, I would say, is probably the biggest open source CFD project that's out there. It has a great community, and so it's been very active for a very, very long time. I think the project is about 25, 30 years old at this point. It's an open source toolbox that's written in C++, and it's distributed under the general public use license, or the GNU license. Okay. And so OpenFOAM is great. It's been used to do a lot of really great work. A lot of great research is based on OpenFOAM, but you kind of have all the downsides of being an open source code. Mainly that there's no graphical user interface. And so, the way that we use OpenFOAM is that you kind of have to know a little bit of coding, and you kind of have to be familiar with a Linux interface. And so I think that'll be kind of the big step up for most people here is that, using Linux for the first time. And if you've never used Linux, it's going to be very different, I think, than what you're used to. Linux is a whole nother operating system. So I think most people are familiar with Windows and Mac. Linux is kind of the, I would say kind of the odd cousin that, that not people talk about a lot of times. But Linux is great for open source projects. And so maybe something you didn't expect from this class is that you'll be learning a little bit of Linux along the way. But that is something you can put on your resume too. And that's something that employers actually like if you do have experience with the Linux terminal. Okay. All right. So to set up an OpenFOAM simulation, you have to set up this kind of very strict kind of file directory. You have to have these files in the right places. And all of these files are written in basically text code. Okay. But don't worry, we'll kind of cross that bridge when we get to it, but just kind of want to send a warning now. Okay. Any questions on this before we jump to the syllabus? Okay. All right. So hopefully that kind of gives you a little bit of sense in terms of the structure of the class, in terms of what to expect. So, the first half of this semester, I would say for the first 7-8 weeks, we'll be doing mostly theory. And so that will be kind of more pencil and paper, traditional kind of note taking. There will be a little bit of MATLAB sprinkled in. And then the second half of the class will be focused mostly on OpenFOAM, to help prepare you to do your final project as well. Okay, so let's talk about the syllabus. Okay. All right, so first thing I want to talk about on the syllabus are my office hours. And so office hours are going to be 3 days a week. So I will be physically in my office during office hours, so I'll be E220, but you are also free to join via Zoom as well. And so there are Zoom links on the course website for you to join office hours for each of these times. Okay. And my office hour times are Monday, Tuesday, 2:30 to 3:30 p.m. So that's basically right before lectures on Mondays. I also teach at 4 p.m. on Tuesdays, so that's right before the lectures on Tuesdays. And then Thursdays from 1 to 2 p.m., right? So I know what everyone's thinking, these times are not ideal. I know usually I don't like to stack. All of these are kind of stacked in kind of the early afternoon. Usually I like to have a little bit more variety in my office hour time. So I'll have one in the morning, one in the evening, one in the mid-afternoon. But one thing that just happened to me recently is I have a kid now. and that kind of limits my availability. So in the mornings, I'm usually taking care of the kid before my wife kind of prepares for work. And then even in the evenings, I have to kind of hurry home and give my wife a break from taking care of the kid too. So I'm really kind of only here kind of late mornings up until the early evenings. And so that's kind of when I can do the office hours. So, with that in mind, these are not the only times I can be available because I know you guys are all really busy. And so if none of these times work for you, and you do want to talk to me, you have questions on the homework, you have questions on the content or the exam, just send me an email and we can set up a time to meet, probably most likely over Zoom, maybe sometime in the late evening or early morning or, whenever time works. Okay, so don't be afraid to reach out and set up an appointment. But at least these will be the times where I'll be available for sure for office hours. Okay. Next, we have the course level learning objectives. And so these are learning objectives that I have that are kind of organizing the entire course, right? So not only do we have the learning objectives for every individual lecture and every individual class, but these are learning objectives that are kind of encompassing the entire semester, okay? So everything that I do kind of is organized by these learning objectives here, right? So I won't go over them right now because I think, right now they're probably not going to make a lot of sense. But by the time the semester ends, you'll be able to go back to these and hopefully say that, yeah, I can do all of these things here after this course. Okay, let's talk deliverables. And so, so there are 7 homework assignments planned for this class. Some of those will be open forum activities, and so those will be in the second half. 2 midterm exams and 1 final project. Okay. So the homework assignments, please do them all. I don't assign homeworks to waste your time or to give you busy work, and so they all kind of have a purpose. But I do understand that things do get crazy during the semester, and so the lowest homework grade will be dropped. Okay. One thing I'll also say too is that homeworks will be graded purely on completion. And that's mostly just because we're going to have a variety of different homework assignments in this class. So we'll have some homework assignments where you'll be doing a lot of pencil and paper calculations. You'll be doing some assignments which will be purely in open foam. And so having kind of a uniform grading kind of rubric between them is kind of difficult. And so I'm just going to say that all the homework is based on completion. This is an elective anyway, so everyone chose to be here, right? And so hopefully that, you guys are excited to kind of do the work. So, and so I kind of trust you guys are kind of doing the work. So I'm just grading the homework based on completion. Okay. Midterm exams. The midterm exams will not be cumulative in the sense that each midterm exam will probably cover about maybe 6 or 7 weeks of content. But the final project will require knowledge that was gained throughout the entire course. Okay. And then last thing I have on the slide here are the planned dates for the midterm exam. So first midterm is planned for Monday, March 9th. Second midterm exam is planned for Wednesday, April 22nd. Those are going to be in lecture here. And the final project is going to be due the Sunday at the end of finals week, Sunday, May 17th. Okay. So the final project due date, I can't really change. That's kind of just, that's the latest I can have it and still have enough time to grade everything. But the midterm exam dates, I am flexible with. So I know it happens every semester, and I know I get accused of this every semester, but it doesn't happen. There's no conspiracy. I don't collude with the other faculty and say, hey, let's have all our exams the same week. But I know it happens. I know all the exams tend to fall on the same week. So if you guys need a little extra time to study, you have kind of everything going on the same week, just let me know. I'm always open to kind of push these back to kind of help you guys out. Okay. Okay. Let's talk course grades. And so, out of the deliverables, this is how everything's gonna be broken down. So homework is gonna be worth 10%. Your 2 midterm exams together are gonna be worth 60%. And the final project is gonna be worth 30% of your grade, okay? Now, your 2 midterm scores, one of them is gonna be worth 25% of your grade. The other one's gonna be worth 35%. And the way I kind of choose which exam goes where is whichever exam you score better in, I'm going to make that one a higher percentage of your grade. So, so let's say you take the first exam, you do really well, then that one is going to be worth 35% of your grade. But if you take the first exam, let's say you don't do so well, then, you kind of have time to make it up and then some for the second exam. Okay? So that's just to kind of give you a little bit of flexibility, just to kind of make you feel like, you're never really truly out of this class. So there's some extra points there as well. Okay. And then based on everything that's, after all the grades are in, I assign letter grades based on, I think this is a pretty standard breakdown here. So 90% and above are A's, 80% above are B's, 70% C's and D's, so on. Okay. The last thing I'll say here is that while I don't curve this class, at least not in a traditional sense. And so I haven't decided beforehand that I'm only going to give 10% A's and so on and so forth. But I do grade scale. And so what that means is that, by the end of the class, after all the grades are in, if the course average, and so the average grade for everyone in the class, if it's below a certain threshold, and usually for my technical electives, I put the threshold a little bit higher. If the threshold is below a B minus, what I'll do is I'll add points to everyone's grade until the course averages up. And so let's say the course average is about 75%, all is said and done. I'll probably add about 5-6% to everyone's grade to get there, and then assign the letter grades after I apply that scale. Okay. Any questions on this so far? Okay. All right, textbook. So we're going to be using a couple textbooks. Neither of them are required, but they are good references. So both of these are very good. First one is a textbook by Parviz Moin. So this is kind of the first textbook that we'll be using in this class. And so it's kind of an introduction to numerical analysis. Just so I know for a lot of you, this is kind of your first numerical analysis computational engineering course. And so, we're going to start with the fundamentals. So this is a great textbook. It's actually very small. It kind of just looks like a paperback novel. But this is the one that I used in grad school too. So it's a very good one. I met the author for this book actually too. I met him at a conference. I didn't expect to, and I was kind of picking out on cookies at the time. And he's like, "You must really like cookies." I'm like, "Yeah, chocolate chip are my favorite." And so, he probably doesn't have the best impression of me, but his textbook is very good, so I keep using it. And so the second textbook that we're going to use is a textbook by Mukamad, The Finite Volume Method for Computational Fluid Dynamics. This is a pretty fundamental textbook in CFD. It's pretty comprehensive. It's a Springer textbook, and so it should be pretty widely available. And so this one's a very good one as well. Okay. But neither of them are required. And so, I'm going to post all my lecture notes, all the homework assignments. And so, there's nothing really to use the textbook for if you feel comfortable with that. But if you do want to see some extra detail in the theory or some extra examples, then the textbooks are good for that. Okay. And what I always tell people is, don't pay full price for a textbook. Never pay full price for a textbook. Find a cheap one, or, if you're tech savvy and, you want to do a little bit of Jack Sparrow on the internet and find a free one. That's good too. Okay, programming. And so, naturally being a course in computational fluid dynamics, there's going to be some programming involved. So on the one hand, we're going to be using a little bit of MATLAB in the first half of the course. That's just to kind of drive home some of the theory that we're learning in terms of finite differences and finite volumes. I don't plan on making it an emphasis. And so, you're not going to have none of the projects are going to require MATLAB. But it is useful to use MATLAB to really see how the finite difference method works, how the finite volume method works. Okay. So I think someone sent me an email already that, they're kind of feeling a little bit uneasy with the programming. There will be some MATLAB programming, but it's not going to be an emphasis. Okay. I think probably the bigger I think, programming aspect, or the bigger computational aspect, is going to be the Linux stuff that we're going to do in the second half. And that for sure, I know that, probably no one or very few of you actually have direct experience with Linux. And so that stuff we'll be learning from scratch for sure. Okay. But I do expect you to at least know how to open MATLAB, how to do the basic kind of, basic for loop, basic if statement, define a variable. And so I am going to be assuming that you do have that kind of basic information when we do the first half of the class. But, just know that the MATLAB is not going to be a huge emphasis. Okay. So if you're a little bit rusty on the MATLAB, don't worry too much. We are going to do a little bit of review, and it's not going to be a huge emphasis. Okay. And the Linux stuff, because it's going to be everyone's first time, we'll be doing that one from the basics. Okay. Course website. And so, we'll be doing a tour of the Canvas site after this, but I just want to have a brief slide on this. So any content that I make for the class, I'll be posting on Canvas. And so I don't hide anything from you guys. All my lecture notes, homework assignments, homework solutions, exam solutions, study guides, open foam tutorials, handouts, Linux tutorials, I'm going to put it all on Canvas. Okay. And so, you should be checking the Canvas site regularly for these things. Okay. If anything, just to download to have as a resource for the future as well. Okay. I'll be making announcements through Canvas as well. I think all the Canvas announcements are emailed directly to you. And I think everyone, I don't think there was anyone on the wait list. So I think if you're in this classroom, I think everyone should be enrolled and on the Canvas site. So you should be getting my Canvas emails. And so I've only sent one so far. But yeah, just to let you know. And also, the Canvas site is where you're going to find the Zoom links for attending the lectures and office hours as well. Okay. Quick note on the lecture. And so, obviously what you can see is I am streaming this lecture on Zoom right now. You are free to attend the lectures on Zoom. So I don't take attendance or anything like that, or even, honestly, when I'm up here, especially only getting 3 hours of sleep with a newborn, everything is blurry out there. So, I'm only 80% certain that there's people in this room right now. So if you're on Zoom, it doesn't really make that much difference to me. The only days that I do expect you guys to be in person are the exam days. And so the exam days, you do need to be in person because I'm not administering that over Zoom. All right, course policies. And so these are kind of the last of the policies that don't really fit into their own slides. Homeworks, I do accept late homeworks. Although every day that the homework is late, I do assess a 10% penalty. So I think this is pretty standard. So again, remember this, the homeworks are graded on completion. And so if you're 1 day late, that's a 90%, 2 days late, 80%, so on and so forth. Okay. Regrades, I do regrades. And so I think for this class, it's really going to be only applicable for the exams. So if I make a mistake grading the exam, definitely let me know. It can be as simple as, I just added up the points incorrectly. Or, maybe you had questions about why I took off points. And so I'm always happy to answer that. The only requirement that I have for regrades is that, you talk to me within a week after I give it back to you, right? So typically, when I give the exam, usually it takes me about a week to grade the exams. I'll give the exams back to you a week later, and then you'll have a week after that to come back and ask for any regrades or any clarification. Okay. Emails, I'm usually pretty quick with emails. And so if you send me an email, I'll respond to you within a day or two, maybe same day, maybe within 5 minutes if I happen to be on the computer. The only thing that I ask is that you include EGME 436 in the subject line. Okay. So I get a lot of emails. And so on any given day when I wake up in the morning, I have 15, 20 emails to answer. So usually what I do and the way that I kind of organize is that, I'll literally go to the search bar in my email program. I'll search the class. So I'll search EGME 436 and I'll answer all the 436 emails at the same time. And so it just kind of helps me to kind of organize my inbox just because, I get a lot of emails from the school and everything. And so if you do that, I promise you, I'll get back to you in a time. Okay. All right. Any questions on this so far? Yeah.
When the time comes, are you gonna have like a day where you go over how to install OpenFOAM?
Yes. Yeah. So we'll be doing, it's a little bit complicated to install OpenFOAM because you do have to install Linux on your system as well. So we'll be going over all that in class.
Are we expected to bring our own laptop to do the Linux stuff?
I think probably for those ones, we might do Zoom lectures for those ones, just so that you can kind of have the Zoom open and have your lecture on the laptop here. But if you're going to be in class, then yes, just because there's no computers in this room. So if you want to follow along in the lectures, then we'll do that. But we may just do virtual lectures on those days. Okay. I forgot this. So this class is a technical elective. And so, this class is open to enrollment for both undergraduate and graduate students, and also undergraduates who are taking it for graduate credit. And so if you are a grad student or if you want to take this course for graduate credit, there is a requirement that you do have to do an extra assignment. And so, please don't forget that. And so I haven't decided what the extra assignment is going to be. Usually for these types of classes, I just have it be an extra component of your final project. And so that's probably what's going to be. And so, I'll release the details of the extra assignment later on. But if you're just an undergrad, you're taking this for your BSME, don't worry about this. This is really just for the grad students. Okay. So last thing I want to talk about before we take a tour of the Canvas site is academic dishonesty. Okay. Probably the most uncomfortable conversation I have to have with you guys, but we we have very strict policies on academic dishonesty, both at the college level, university level, department level. Basically short stories that it won't be tolerated. So any form of academic dishonesty, any way that you're getting someone else or something else to do your work for you, that counts as an act of academic dishonesty. And of course, that includes use of AI tools like ChatGPT. Okay. So I take a pretty hard line stance towards AI tools. I think it's fairly simple. I just don't allow it at all. And kind of my rationale behind that is that, you know, if this were a situation where you were doing work for a company and your analysis is just going to be used and sold off and just be used to make the CEO of your company richer, then like, yeah, I would say, who cares? Use AI. You know, you're not expected to really gain anything from that type of work, right? But a classroom is different. And so a classroom, you know, the reason you're taking this class is to obtain skills and knowledge that you're going to apply, right? And end of the day, you know, if something else or someone else is doing your work for you, you know, you're just not getting the skills and knowledge, okay? And, you know, I know that, you know, probably after this class, you know, you go out into the world, you know, AI is going to help you run CFD. That's just the reality that we're going to live in. But, you know, like I mentioned before, you know, when you guys leave this class, you know, I want you guys to feel like you're an expert in CFD. And part of being an expert is not only running the software, but also, you know, looking at, you know, CFD results that someone else may have computed, or CFD results that an AI helped you do, and being able to assess whether or not these results are actually accurate and reliable, okay? Because it's one thing to actually do the simulations, it's another thing to actually curate and assess simulations, okay? And, you know, I'm of the firm belief that you can't really do that unless you kind of go through the grind, you go through the struggle of, you know, doing this stuff yourself, okay? I know that AI can probably do a lot of the work in this class. It's probably good enough to do maybe like 6 or 7 out of 10, right? You know, but the point of being in a class is not just to do the work, it's to actually learn the material. And so, you know, after this, yeah, go wild. You can use AI stuff, but, you know, while you're in the classroom, I would say, you know, do the work yourself. You know, I know it's a struggle. I know it's painful. I know it's time consuming, but, you know, I promise you'll gain a lot more out of it by doing this. Okay. And, you know, my promise to you guys is that, you know, my job here as an instructor is to help you guys succeed and gain as much from this class as possible. It's more than just, you know, for me, it's more than just assigning the grades at the end, right? And so I want you guys to all feel like you've succeeded, you've gained something valuable from this. And so, you know, if you ever feel like you're struggling in the class, you ever feel like you need to use something to catch up or do the work for you, you know, please, I just ask you to come talk to me first. And so, you know, my job here is I'm not going to judge you. I'm not going to look down on you for anything like that. You know, I've had people come up to me and said, you know, I've been absent for the last 8 weeks. I know the midterm is tomorrow. You know, what can we do? And so I said, all right, you know, let's figure it out. There's no judgment or anything like that. I promise you I'll do everything I can to help. Okay. So that's my promise to you guys to, you know, to help you guys succeed in this class. So that's what I feel like my job is here to do. Okay. So before we go to the course website, let's talk about your first homework assignment. And so some of you have already done this, which is great. But the first homework assignment is simply just to send me an email and introduce yourself. And so, you know, we're going to be stuck together for the next 16 weeks. And so, you know, I would prefer it to be, you know, kind of a comfortable experience to get to know you. So please send me an email. Tell me a little bit about yourself. You know, the bare minimum is just tell me your name, your year, your major. I think most people here are going to be mechanical engineers, but, you know, there might be someone else taking outside. And I'm always surprised by that. Okay. So I have 4 questions here. You know, you don't have to answer them. You know, I kind of just have those questions there as kind of a conversation starter. Just because a lot of times, you know, I'll meet someone and like, oh, tell me about yourself. You know, like, where do I start? You know, I've lived here for 35 years. So I don't know where to start telling about myself. So I have those questions as kind of like, you know, conversation starters. So feel free to answer them if you want, or not. And so, you know, if you already, you know what you want to talk about yourself, then just go based on that. Okay. A lot of times I'll get emails that are literally just like, they think this is like a literal homework assignment, and they'll go question 1, you know, what kind of career would you like to have after graduating? The kind of career I'd like to have after graduating is this. And so it doesn't have to be so robotic, you know, just kind of talk. You know, I'm just interested in getting to know you. Okay. Or not. And so you could be send me an email and be like, I have no interest in getting to know you at all. And so I would just like credit for this assignment. I'd be like, all right, I will do that for you. Okay. So this assignment is due by this Sunday, January 25th. And so if you send me an email by then, you will get full credits. Everyone starts with an A in this class, which is, I think, always a good thing. And the only thing I say is, don't forget to include EGME 436 in the subject. Okay. Okay, and so with that, let's go ahead and take a tour of the Canvas site. And so let me go ahead and exit out of here. Let's come to the Canvas site. Okay. And let's view as students so you can kind of see, what we're doing. Okay. Okay, so when you first go to the Canvas site, this is what you'll see. And so this is the home page I've kind of made. So you'll see the name of the course, a little bit about me, class times, class location. Everyone here knows this because you're all here physically. Course description, I think this is from the syllabus. Learning objectives, okay? Syllabus is right here for you on the front page, and so I would definitely recommend downloading this and keeping it within your records. Zoom links, and so if you're going to attend the lecture or office hours virtually, the Zoom links for all of those are here, okay? As well as the times in case you forget. Okay? And then at the bottom of the homepage, you'll see that I've taken the semester and I've broken it down week by week, okay? And so this kind of tells you when the midterms are as well. And so as we go about the semester, these links will become clickable. And so the only one that's active right now is week 1 because we're only in week 1, okay? And so if you click on week 1, you'll see here, this is the page that I prepared for this week. And so I'll make separate pages for every week. And so usually I put these up the Friday before the week occurs. And so this will be up by Friday, or the one for week 2 will be up by Friday morning, okay? And so on these weekly pages, you can see that there's a little bit of a description in terms of what we're going to cover that week. There are all the learning objectives for the week as well, okay? Lecture recordings, and so I do record all my lectures on Zoom. Usually I upload the lecture recording the next day, and so the link for that will be here as well. So if you're looking for a specific lecture recording, say you missed a class, or let's say that you want to go back and watch a certain part of a certain lecture, you can view it here, okay? These are all YouTube links as well, and so miraculously, YouTube has not deleted any of my lecture videos at all, which is surprising. Any homework assignments that are due that week or assigned that week will be here as well, and all the files that you'll need for that week will be here as well. So any lecture notes, any lecture slides, handouts, tutorials, homework solutions will be posted here as well, okay? So definitely check the weekly pages. So these will be updated regularly. And so this should be kind of the first thing you check kind of beginning of the week for, just to get a preview of what's to come for the week and also to download any files that you need. Okay. Okay, so next tab that we have here is the announcement tab. So this one probably you'll never come to just because all of these will be sent to your email. But if you want a summary of the announcements, you'll see it here. Next tab is the assignments tab. And so this will show you all of the assignments that are upcoming. And so right now there's only homework 0. Okay. Only thing I would say about this tab is that, just be aware that there's 2 dates here, although all of you are seniors. And so I'm sure you're all aware of this, but, we have 1 date here for the availability. And then the second date here, this is the actual due date. So the assignment is actually due on this date right here. But usually I set the availability date to be a week after the due date. And that's only just to allow you to turn in late homework, okay? So don't get these 2 days confused. And so, turn it in by this date if you want full credit. Turn it in by this date if you want late credit, okay? Okay, so next tab here is we have grades. And so this is a summary of all the assignments that are out there and your grade. And so this will kind of show you where you stand in the class based on everything that's graded, okay? The grade breakdown is given to you here as well, in case you forget. Next tab here is people. So this is everyone that's in the class. Again, I think everyone that signed up for the class should be in the class. And so, there's no one on the wait list. Okay. Next tab here is the files tab. And so basically anything I upload for the class in terms of, starter code, lecture notes, solutions, handouts, everything will be here, okay? So everything that I post in the files tab will be in the weekly pages. But, if you're looking for a very specific file, so let's say that you're working on a homework or looking for a specific starter code, you can find it here. And so, it might be faster to find it here. But, just know that these are all in the weekly pages. Okay. All right, last tab that we have here is SOQ. So this tab, you can't access this yet. You can't leave me a 1-star review until the semester is over. But I think by the end of the semester, this will become active and you could do SOP. All right, any questions on the Canvas sites? Okay, all right, and so that's everything with the course introduction. So normally this is kind of where I stop it for the first lecture, but we do have to catch up a little bit because we did miss the Monday because of the holiday. So let me switch to my iPad here. Okay, we'll get about maybe a good 20 minutes of lecture done before next Monday. Okay. All right, so this is kind of the usual way that I lecture. So I have my iPad here, I have my my stylus, and I have my notes here. So I do write my notes by hand, and so I think people kind of generally find it a little bit easier to follow. So first day is usually an exception. First day I have the slides just because there's kind of a lot to go over, but this is kind of usually how I'll. Okay. All right, so our first lecture for this class, this is a class in computational fluid dynamics. And so it's really only appropriate that we start with the review of fluid mechanics. Okay. So I have about one lecture's worth of content for review of fluids, and so we'll probably get maybe about a third of the way done today, and we'll probably finish up the rest of it on Monday. Okay. Okay. All right. So this will be a review of EGME 433, a very fast review, obviously, but we're only really going to be covering the essentials of what you need to start doing CFD. Okay. This is more meant to just be a refresher, and so hopefully none of this you're seeing for the first time. Okay, so let's start very basic. Let's start with the definition for a fluid. Okay, so a fluid is a substance that continuously deforms under an applied stress. Okay. The key word here being continuously. Okay. And so we make a distinction between fluids and solids. So solids, if you apply a stress to a solid, it may deform a little bit, but eventually you reach an equilibrium state where the solid no longer deforms, right? And so, for example, let me take the stapler right here, right? So the stapler is a solid object. If I apply a force to it, you can see the stapler goes down, but eventually it stops because it's a solid object, okay? A fluid is not like that. A fluid, if you continuously apply a force to it, it's going to continuously deform, okay? And so the way that we typically call this, and so no one's saying that, oh, the air is continuously deforming out there, right? We say the air is flowing. And so kind of the way that we typically describe this in kind of normal speak is flow. Okay. All right, and so in CFD, we're interested in basically simulating fluid flow. I know there's a whole area of hydrostatics. I think that's probably the first thing you learn in fluid mechanics, but we really don't care about hydrostatics in this situation. Okay, we're really only interested in fluids that are in motion. Okay, and so because of that, we are interested in a very particular property of the fluid, of a flowing fluid called the velocity field. So the velocity field of a fluid base is a vector field that describes to you, the direction and speed of the flowing fluid at every location within that fluid. And so the way that we describe a vector field is that, or the way that we describe the velocity field is that it is a vector field. Okay? And if you remember anything about vector fields from Calc 3, basically at every physical location, we're going to define a vector there. Okay? So the way we typically define this is we define it as a vector field V with an arrow on top. Okay? And this is going to be a function of physical coordinates. And so Y and Z in 3D. Okay. So again, this vector V here, this represents, the velocity, the flow velocity vector. And this XYZ here, these are physical coordinates. Okay. So let's draw this out just so you can kind of visualize it, because I think, describing a vector field is not the same as kind of visualizing it. Right? Okay. So let's do an example here. Okay. So let's say that we have a very simple kind of velocity field of a flowing fluid. Okay? All right. So let's say that we have a flowing fluid that looks like the following. And let me actually use blue. Okay. So let's say we have a fluid flow. So let's say we have flow in like a river or a stream or something like that. Then looks like the following. Okay. That's a good measure. Okay. Okay, so the blue lines that I've drawn here are the direction of the fluid flow in this application. Okay. So we can say this is, maybe fluid flow or flow of water in a stream. All right, so the way that we can describe the velocity field in this is that, first of all, we need a coordinate system, and so we need to have an origin, right? So let's say, well, this is obviously a 2D scenario, so I'm only going to draw an XY coordinates. So let's say we draw the origin right here. To X, Y, okay? So this right here is the origin of our coordinate system. We're using Cartesian coordinates just to kind of be simple for now. Okay. And so based on that origin, we can define a physical point by a paired X and Y coordinate, right? So let's say that we define this point right here. Okay. So this point, we can say that its coordinates are x1, y1, right? Or that x1 and y1 are the distances, kind of the x distance and the y distance from the origin. Okay. And the same thing, we can draw another point here. So let's draw another point. Let's draw this one here. We'll call this x2, y2. Okay. So the requirements to have a vector field is that you do have to have an origin, because you do need to be able to describe kind of the physical locations of every point within the field. Okay. All right. So the velocity field, at each of these locations and at basically any location within this field, we can describe what the velocity vector looks like. Okay. Let's see. Okay. And so let's use dark blue. Okay. So let's draw what the velocity field would look like at these two locations, right? So we're just going to use these two x1, y1, x2, y2. Okay. So at x1, y1 here, the velocity field is going to basically follow the flow. And so it's going to be a vector that points in the same direction as the flow and have a speed that matches the flow as well. Okay. So at this location here, we have, a vector that kind of goes like that. Okay. So we have a vector that kind of points almost horizontally to the right. It's going down a little bit. And so this vector right here, this is V vector at x1, y1. Okay. So that's our velocity at that location defined by our velocity field. And then at this second location here, we can draw another vector that's perpendicular to the field, or parallel, excuse me. And so this vector here, this will be v at x2, y2. Okay. So the idea with the velocity field is that, for any given location within the fluid flow, you can define what the flow vector is going to look like. And a vector, remember, always has, direction and magnitude. Okay. So velocity fields is a concept that, we'll be coming back to continuously in this class, because the main output or the main goal of CFD is actually to produce the velocity field in your flow. Okay. And that's often what we're going to be simulating for. All right. Any questions on this so far? Good. Okay. So that's the velocity field. Although in fluid mechanics, there's another field that we're usually aware of, and that is the pressure field. So the pressure field, similar to the velocity field, is a field variable, and so it depends on the physical coordinates, and so it's going to be a multi-dimensional variable. And so for the pressure field, we usually denote it by a capital P, and again, it's going to be a function of x, y, and z, okay, or just x and y if you have a 2D situation. Okay. And so the pressure field is going to give you the hydrodynamic pressure at any given location within the fluid. Okay. All right, so we have these kind of two field variables that we are going to keep in mind. And these are, along with the velocity field, the pressure field is also a primary output of CFD. Okay. So oftentimes when we run CFD, we'll get the velocity field and we'll get the pressure field as well. Now, pressure is an interesting concept because it's not a vector. Pressure is a scalar quantity. And so what that basically means, a scalar just has magnitude. It doesn't have direction. Okay. But remember, the reason pressure is important in fluid flow is that oftentimes fluid flow is driven by differences in pressure. Or another way to describe it is that, fluid will flow from high pressure to low pressure. Okay. Just to put it very, very simple. Okay. Pressure fields do have other applications as well. If you're going to get into very kind of high level kind of aerodynamics, and so if you're going to be dealing with shocks or wakes or drags, then pressure is going to be important there as well. But just on a very rudimentary level, if you understand the pressure field, you can kind of make a prediction in terms of which way the flow will go. This flow will go from high pressure to low pressure. Okay. All right. And so, like I've mentioned, the goal of CFD, or I would say the first goal of CFD, of any CFD simulation, is to solve for the velocity field and the pressure field in any flow, in a given flow situation. And then usually from those pressure fields and velocity fields, you can compute lots of other really interesting quantities, like drag, lift, shear stress, wakes, vortices, things like that. But step one, always solve for the velocity field and pressure field. Okay. And if you kind of remember from earlier in the class, velocity and pressure, these are basically the active variables of the Navier-Stokes. And so essentially you solve the Navier-Stokes equations, you get velocity and you get pressure. Okay. All right. Any questions on this so far? Okay. Okay. All right. So let's talk very briefly about fluid material properties. I think that will be the last thing that we cover today. So even though fluid is it's a different state of matter, they do have their own properties. Okay. And if you're going to run any CFD simulation, you do need to input these properties because different fluids are going to behave differently, right? Air is going to flow a lot differently than molasses. And so you need to make sure that you input these properties correctly in order to accurately simulate. Okay. And so there's two main properties that you basically have to apply for every single flow. There's usually more properties besides this for more kind of advanced applications, but at the very kind of core basic level, these two properties are the ones you have to input for every simulation. Okay. All right, so the first of these properties is, let's start with density first, so that one's a little bit easier to understand. Okay. So density, hopefully requires no introduction. Density describes the relative mass of the substance relative to its volume. Okay. Right, so there are different substances that have higher density. Usually, those are substances that have very heavy molecules that kind of make up their chemical composition, and there are substances with very low densities. And what's interesting about CFD and just fluids in general is that you have a very, very wide spectrum of different densities. And so on the one hand, you have a very common substance that a lot of industry would work with, which is just air. So air is very not dense. Mostly just because the distance between air particles is very, very large. But you also have, there's also applications for CFD where you work with very, very dense fluids. And so things like liquid mercury is very, very dense. And so there are applications for that where you would want to run CFD. So there's a very wide range of different densities that are available in fluids, and that obviously drastically changes the behavior and the results that you get from CFD. Okay, so the other comment that I'll make with density, one that will become kind of very relevant later on, is that oftentimes we assume that the density of the fluid is constant. Okay. And this is actually a very important assumption because this leads us to what's called the incompressibility assumption. So incompressibility is very interesting. Fluids have this unique property where you can actually compress it. So you can actually kind of effectively squeeze it enough or run it fast enough such that the distance between particles actually becomes affected enough to actually make a difference in the density. So that mostly has applications in aerospace engineering. And so if you start to have very high speed flows, you get to hypersonic flows. Mach numbers 1, 2 around that type of flows, then compressibility becomes a concern. But for the most part, for this class, we're going to assume our flows are incompressible, just because it makes the math just a lot easier. But I did want to kind of mention that here. There are applications where you have a non-constant density. You have density that depends on pressure and velocity. But we're not going to be dealing with that in this class. Okay. So the other property that is important to know for fluids is its viscosity. So the viscosity of a fluid describes how well the fluid essentially kind of sticks to itself. And I write sticks in quotation marks because that's definitely not the scientific way to describe it. There's no textbook out there that will say it like that. But I think it's kind of the easiest way to visualize it because if you have fluids that have very high viscosity, generally what you associate with those are fluids that kind of feel very, very sticky, right? And so, you think of like honey, you think of like molasses, right? So these are fluids that kind of really stick to itself. And the way that we describe it is through its viscosity. Okay. Okay. Let's see. And so mathematically, viscosity plays a role in terms of how the strain rate and shear stress are related to each other. And so there is a formula from fluid mechanics that looks like the following. So we have tau. So tau here is an expression of the shear stress. Okay. So the shear stress is basically any kind of force that the fluid can impart on another object through shearing, basically. So if the fluid kind of flows past an object, the amount of force that you kind of feel, the friction force, that's the shear stress. Okay. And so this is equal to the viscosity multiplied by the strain rate. So the strain rate is simply just a derivative of the velocity. Okay. And so oftentimes, shear stress is a quantity that people are interested in. And so in order to compute shear stress, on the one hand, you need to know viscosity, but you can see the other thing that we need to know is the derivative of velocity, which you can get from the velocity field. Okay. Okay. All right. Any questions on this? All right. So it's 5:15. So let's call it here. So when we come back on Monday, we'll kind of continue on with a review of fluids, and so we'll start reviewing the Reynolds transport theorem. Okay. All right. So thank you guys for coming today. It was great meeting you guys all. Kind of a jam-packed first day, but hopefully it was good. So I will hope you guys have a good weekend, and I will see you all on Monday.
Yeah, really like live opening there or the paper stuff. Going back to the
Yes, DUD. Yes.
What are you gonna do?
I'm gonna see. Depending on that, take a while. But I'm gonna see if we can the school activity. Although I tried to.
Yeah.
So we'll see. Generally, you don't want to fight fire with fire. Yeah, we'll see. So you may talk about fire. You on? Yeah, I don't think this might be the first time. So if you add in the clock, there's no rush in taking it, because you're not taking it 500 courses, right? So I would definitely recommend that at least that. And so right now, I would take the time to take these kind of courses.
Loading and then cellular extraction. I try to get
Take courses.
if I can hide all the components are inside.
I mean, you got it to.
I usually do. Okay. So I only have to come back. I remember if it's anything. I think. I have a question. After you emailed you and. But like,
Yeah.
but the steering column, the steering. All that, you know, like just. Not last semester. So I kind of just had that out of my head on his graduate, but the following semester I took 410, the rocket and
3 hours.
combustion. So all those were eligible for grad credit, but I didn't know about that condition thing, right?
Yeah.
So this semester I enrolled in this 438.
Yes,
315, because I don't need any more tech like this for my undergrad, but I shouldn't take. My question is, there's like a different petition when you're a grad student. I think on the site it said when you're a grad student, you have to petition up to date previous. But I didn't use the grad credit like extra thing on the 410 because I wanted that area. So is that completely off the table?
Unfortunately, yeah. So if it's semester's already done, you can't go back. It took me like 3-4 hours ago. Semester 2, the 315. I would.
Well, I know, that's what I'm saying, it's like, I'm in a weird predicament because on the website, it says a different thing, like what you sent him, you know?
Yeah.
Like, I don't know if you've seen that, but.
32
gigabytes.
Maybe the mesh. The mesh was.
From here,
It didn't crack or
petition for a 400, 500, and I know on the petition you sent him included like that requirement, you know?
Yeah.
But on that
Oh, you're
one,
gonna
it
ask
didn't, it just said you.
I'm just gonna ask him
student
something
and up to there was another assignment, so you're 100% certain that 410 can't roll into grad credit.
Well,
But I-
because the issue is that the class is already done. And so
Yeah.
usually the grad assignment.
Figure out.
It says moving like ghost.
No, like, it's literally like. Yeah,
I get the.
I mean,
in there.
I don't know what she counted it as. I ended with like a pretty high score in that class.
Yeah.
So like, straight with the card. A lot of times they count it at like 5%. That's why I'm like, I don't know. Like, I don't know if do you make the final say or does it like a department do
We
stuff?
do, we have a graduate student advisor. It used to be Dr. Merrill, actually.
Okay.
But since he was, I think Dr. James is handling it.
I've already reached out to him, but you're saying like you're like 100% sure it won't.
The class are done. Maybe we might.
That's screwed me up a little bit for.
Like,
I might send you an email, I guess, for 541.
Okay. Well, why 41? Why 41?
No, I know, but I'm just saying, I'm just planning on keeping 541 for later.
Yeah.
And taking the 350 and substituting.
I think that was 19.
Yeah, let's say it wrong, I guess, but I still will reach out, but you'll hear me say, oh yeah, you were right. But maybe, I don't know.
Yeah, might as well.
Might as well, like, screenshot the website, but I guess that's what you're saying, so, okay. So this one, I guess
This one for sure.
petition, yeah, I still got next week, but yeah, okay. Thanks.
Yeah. Hey, Derek.
So I'm at 16 minutes right now, and
Okay.
remember that undergraduate, project, individual project?
Yeah,
I'll be here.
That was me at 19, so I
Oh.
was wondering how I can get the extension.
So I'll be.
So you can, so you search Cal State Fullerton excess unit petition. That's the petition you have to fill out.
Is it environment and decisions by itself, or do I email it to the?
I don't know how it used to be just a form you print out and they sign it, but I think they're trying to move everything digital now.
Okay.
But the thing is, that form not only has to be approved by us, but it has to be approved by the university. And usually for those situations, they'll only approve it if you need the extra units to graduate. So if you're just taking the extra units, just cause they may not approve it.
Oh.
But you can try.
Okay.
I think it's worth it. But yeah, but that's the petition. The search of excess unit, it's a very specific form. If it's digital now, I might just get an email about it, but if it's a PDF, then you can send it to me.
Okay, sounds good.
Yeah.
Thank you.
Yeah.
It never goes longer
Hi,
than.
so I just had a quick question about something in OpenFOAM. So I've been running for formula.
Oh,
I was getting the whole car in there.
yeah.
So I was trying to get the whole car. As two SCL files, one with the whole car and then one just a rear wing so I can run layers on there and
Yeah,
not have it crash.
Yeah.
But every time I get it into OpenFOAM and peer review, like I'll check it in peer review, it's shifted to the right.
Oh,
So I'm not sure if that's something in like my code or if that's.
usually so the way it works is that the OpenFOAM will take the coordinate system from one of the files.
Yeah.
And so probably what's happening, so you're trying to combine the two files.
Yeah, so I'm literally just taking like the master assembly of the
Yeah.
whole car, hiding everything and then saving it as like hiding everything except the rear wing and saving it as rear wing
Gotcha.
SCL.
Yeah,
And then I'm doing the opposite, just hiding the rear wing and then keeping everything.
yeah,
And I'm saving that. So it should be the same origin points.
right.
But for some reason it's not.
Yeah, because you're converting to but these are SolidWorks assembly, you're
Yeah,
converting to
yeah,
STL, right? Sometimes when that happens, it could reset the origin point, because STL is actually a very simple file format.
Yeah.
So that, I would probably maybe look to see, like, there might be an online tool you can see to like upload an STL and kind of see where the origin is.
Mhm.
You may be able to modify it there.
Okay.
And so you may have to kind of manually do that just to make sure everything.
Yeah, everything lines up. Yeah.
That's what I would look into.
Because like just to like get like a simple run out,
Yeah.
I downloaded